speaker is Ben Williamson from the University of Aberdeen. And Ben is going to be talking to us about his experience of using, we'll call it an integrated instrument package, not perhaps quite on the same scale as Brian's that he described earlier on, but this is as far as we've got.
Great. Well, thank you, Ian. I realise I'm in the methodology session, so I'll try and keep this to techniques and just enough results to try and show you what kind of data you can get from the FLOWBEC platform that we've got so far. So thanks very much to all my co-authors here. The FLOWBEC consortium is huge, led by Paul Bell at the National Oceanography Centre at Liverpool. So the FLOWBEC upward-facing sonar platform, you can see it down here on the right-hand side, being manhandled into the water at the EMEC test site in Orkney. It's an upward-facing platform that monitors the entire water column. So from the seabed right up to the surface, we're looking at plankton, fish, seabirds, and marine mammals. So a range of physical levels and a range of multi-trophic levels. And the idea is that we capture the movements, the behavior, and the interactions with marine renewable energy devices. We talked a lot about different solutions, cabled or not. The FLOWBEC platform is self-contained, which makes it portable between sites. There's zero infrastructure to install, so there's no cables, there's no anchors, there's no marker buoys. You just take your boat out at near slack water, lower it down to the seabed. The whole deployment process is designed about 20 minutes for the amount of slack water that you get at these tidal sites typically. And then recovery is by an ROV, flying down to land on the black platform. You can maybe see at the back, hooking onto it. Recovery, we've managed them all in less than an hour, again, in slack water. So the idea is it's quick and easy to deploy. It means you can carry out baseline studies around the site, pre-construction, pre-installation. It means you can move around the site to get an idea of what's happening spatially as well. We designed it to continuously sample a springy tidal cycle, so that's a 2-week period, at a resolution of several measurements per second. Working out that what we see in this 2-week period, we can then work out how that applies to longer timescales. The FLOWBEC platform is complemented by hydrodynamic model data, as well as above-water radar and bird observations. So we're getting a complete picture of what's happening in these sites, above the water, underneath the water, and then for the birds as they come back out. And I think most importantly, as Ian says, this is a first-stage project, but it's field-proven. We've had 5 2-week deployments at EMEC, both at wave and tidal energy test sites, both adjacent to tidal energy structures and further away to gather control data. So we've got some real data that we're working through on the analysis at the moment. So you can see the platform down here on the left-hand side, deployed at the EMEC tidal site. I wonder if this will work. Okay, so we'll go through the instruments one by one. First of all, we have a Simrad EK60 echo sounder. So that's these 3 beams here coming from the seabed up to the water surface. And that gives you bird and fish abundance. You can also look at school behavior. It's got a long history of being used for boat-based sonar surveys. So there's a lot of literature on using multi-frequency target identification. How your fish show up on the different frequencies. You can use that to try and get down to a species level of identification. We can also use this to look at the morphology of turbulence. So please go and see Sean Fraser's poster upstairs to have a look at that. And plankton as well. We synchronize this with an Imagenics multi-beam sonar, so having multiple acoustic instruments on the same platform, very important to avoid noise between them. So we've got 1 ping per second for the EK60, but for the multi-beam, that's this green swath here. It's 120 beams coming out throughout the whole water column. The lowest one's aligned with the seabed, and we deploy within 20 to 50 meters of a tidal turbine structure. So the idea is that this swath here envelopes the tidal turbine structure, all the way up to the water surface, and pinging at several frames per second, you can track targets, quickly diving seabirds, coming down from the water surface, any interactions with the tidal turbine structure, and then back up to the surface. I say that target tracking, we'll come on to that later on, and when I say avoidance behavior, this is where we get down to our definitions. So what I mean here is evasion. We're just looking within this 50-meter range at any last minute, for example, swerves, changes in vertical distribution. We also have an ADV that gives us local current measurements right on top of the frame, as well as temperature, and a fluorometer as well, which measures chlorophyll as a proxy for phytoplankton. So what we're looking at here is, can we relate any variation that we see in the water column to these lower cost instruments to later on try and reduce the cost of monitoring. We'll have a look at some of the example results to give you an idea of what you can get from it. So first of all, this is the multi-beam. The swath here is aligned with the tidal flow. So in the tidal energy site, the majority of the water is moving back and forth in this direction. The idea being that passive targets being swept with the tide, will move through the swath, and targets which are actively swimming against the tide, you'll pick them up for a long duration. So what we see here is a turbine structure on the seabed. This is the open hydro stationary turbine, the test turbine at NERC from our first year of deployments, and a large target tracked with a multi-beam. From the side of it, we think it's a marine mammal. We'll come on to classification later on, probably a seal here. So the colours show you the history at the time. Blue was 7 seconds ago, coming through green to red, so the target's moving from right to left on the screen as you look at it. Now we'll move to the wave energy side, and this is example EK60 data. So now it's 9 minutes along the x-axis, pinging from the seabed up to the water surface. And when you see targets here, this is persistent above the frame for a certain duration of time. And what we're looking at is a school of fish near the water surface. And what's exciting are these predator-prey interactions and how they might vary around tidal wave energy sites, and they might be affected by the devices themselves. So what we're looking at is guillemots and razorbills diving beneath the fish school, coming back up and feeding on it. I sense skepticism, so ground truthing is very important. Are these blobs really guillemots and razorbills? And that's where James, who you heard the talk from before on the Seabirds, comes in. He's done a huge amount for the project on ground truthing, using shore-based bird observations, looking at the area above the frame to record what he's seeing on the water surface, so we can correlate that to behaviour, which we can detect on the acoustics underneath. The idea being that, yes, you need this ground truthing for your first deployment, yes, you need all these instruments, but the algorithms that we're writing we can then apply to further sites without the need for ground truthing. Okay, we said that bit. So remember in your mind this bit on the right-hand side, the guillemots and razorbills diving beneath the fish school, and cross your fingers because it's a video in PowerPoint, so we'll see. Okay, it's a bit jumpy, but this is the synchronized multi-beam footage of those diving seabirds. It's a loop of just about 10 seconds. What you see is the school of fish at the surface, and here are the birds diving down beneath. This is just raw data. It gives you a kind of an idea of the data quality you can get, the noise particularly, the reflections, the artifacts in it, the challenge of the data to pick out these targets and identify them. We've seen some amazing acoustic footage throughout the day, and yes, this is a very low quality, but more importantly, a low cost and a low power consumption multi-beam. And that was chosen deliberately. The cost, of course, to get down the cost of monitoring, that was a big thing that came up in the workshop the other day. But power and data is very important, of course, if you're self-contained, as we came up before. To get 2 weeks of continuous recording, 8 pings a second, yeah, it needs to be low quality. But what we proved later on is that this is adequate for the data that we're trying to get out of it. So target tracking is something that we're looking at the moment. This is just an example, back to the tidal site now, deployment next to the Atlantis tidal turbine. So this is of interest to the planned major deployments in the Pendant Firth. Here it's a tripod base with ballast blocks that fits onto the tripod legs here. So what it looks like in the multi-beam is the center piling here, one of the ballast blocks here, the FLOWBEC frame deployed here, about 25 meters from the turbine structure. Blades weren't fitted to the turbine at the moment, so what we've done as a proof of concept is just to put the dashed lines on here at the expected blade radius to give you an idea of scale. The water surface is way up here at about 40 meters. And what we're looking at again is a fish school passing through the multi-beam swath. So by using target tracking, we can look at a 2-week deployment, and we can pull out all of these different targets, rather than using manual processing, having to sit through this data. We talked about data mortgages as well. What we're developing are the tools to pull this out autonomously. So first of all, target detection. Then we look at the EK60. This is what a fish school looks like on the EK60. Using the frequency response, the difference between these frequencies, to try and guide classification of fish species. Target tracking then comes in. So again, we see the evolution from red to blue of the fish school passing through the frame. And then finally, the multi-frequency analysis. So this is just an example from the literature. The School of Mackerel, we heard about this earlier on, how the frequency response varies, looking at the 3 different frequencies. The idea being that there's going to be a huge amount of fish passing through the site, but we've heard about the ones of conservation concern. We can start to weight what's happening in the site by, for example, the salmon that we heard about before. give you an idea of where we can use this information, if we look at a vertical distribution next to the Atlantis tidal turbine structure, what we're looking at here is something similar to what Gail presented earlier on, the vertical distribution of targets. We've got the turbine structure down here, and it's a solid green, the expected blade radius, and these are about 4,000 targets that were tracked over a full 2-week deployment. If we zoom in just on the seabed part, and we see that, yes, up here there's a big bias towards targets at the water surface, but when we zoom in, there's a huge amount still going on down here over the 2-week period. So these targets are at a height where they're likely to interact with the turbine or the blades when present. And that's important. What we saw on the previous slide were all targets. What's important is classification, saying how many of each different target category, or eventually down to hopefully a species level, particularly for fish, are at a height where they're likely to encounter the turbine structure. So these are the sorts of targets we can pick up. At the moment, we're just looking at large schools, small schools. That's where measures of the school morphology come in. Measures of the multi-frequency analysis come in. Single targets, so this is larger individual fish, actively swimming or passively being swept through the site using the water for transport. And diving birds. We've heard a little bit about it. I think we'll hear a bit more tomorrow about the importance of diving seabirds and the risk of collisions in these sites with the turbine blades. So the characteristic U-shaped dive and the predator-prey interactions that we saw earlier on. We can then pick out these individual categories, the vertical distribution. Bear with me, that's good. Okay, so with it being a methodology session, I thought we'd just try and look at some of the benefits and the limitations, so you can try and see how the FLOWBEC platform fits in with all the different techniques that we've heard. With this just being one part of the jigsaw, how it all fits together on a site-specific monitoring basis. So the FLOWBEC multi-beam gives you high range, about 50 meters, good detection, irrespective of visibility, irrespective of illumination. So just from the tidal site results that we've got so far, we see a huge amount of fish activity at night time. So we can gather data 24 hours a day. Small data volumes, we heard about data mortgages. This is the active choice to choose a very basic multi-beam, and therefore self-contained, low power in terms of data, and power is possible. And also real-time processing is feasible. We're developing the algorithms at the moment, applying them to our 5 2-week deployments. The idea being that with the controllers that are mounted on board, we can be processing this data as it comes in. Of course, there's limitations. I'll try and preempt some of these. Limited detail for species identification, is certainly accepted. There are blobs on the sonar, and you need to try and use your complementary data sets, your ground truthing, to try and get this down, first of all, to target categories and to species. And observation of the final 1 meter interaction. We can see evasion behavior, we can see the vertical distribution to inform behavioral models, population models, but the final 1 meter interaction, whether there is a collision and the severity of the collision, that's where we see it fitting with the other packages, the other sensing methodologies that we've heard about. And of course, is there any behavioral response to the acoustics? So I think we'll hear from different colleagues about the potential effects of frequency output and the multi-beam from the EK60 on, for example, seals or marine mammals. So here we've got the option to duty cycle, to use just a select batch of instruments at short periods of time, turning off frequencies of interest, using the other instruments to work out if we're seeing any changes, what's the effect, if there are any changes, any behavioral modification. But one other solution is to use this multi-instrument integration. So I won't dwell on it, we've heard a lot about it from different people, but just to say that this is where we see the future as well going. It's probably a similar diagram that we've seen with Brian, so trying to integrate all these different instruments, and this is what we'll come onto in the collision workshop on Friday, I think, if you're able to join us, to try and combine large scale with fine detail, reducing data processing and archival, trying to cycle passive and active acoustics, first of all just cycling, but then intelligent triggering, and then finally, remember that limitation of the last 1 meter interaction, was there a collision, and the species interaction, so triggering a camera for ID and detail. So just in summary, the FLOWBEC project's investigating the ecological effect, both installing the baseline studies, infrastructure monitoring, and operating marine renewable devices to determine collision risk probabilities and define vertical habitat use. We can use this to increase our overall environmental understanding of mobile animal use in these high energy sites. to therefore inform marine spatial planning, device design, licensing and operation. As these individual devices are scaled up to arrays, particularly exciting for the Pent-Firth array at Mayhem, and to increase the predictive power to eventually try and reduce the monitoring that's required to reduce these full suites of instruments into just the bare minimum, using the algorithm developments and the ground truthing that we've done before. Thank you very much for listening. I'd like to thank my co-authors and sponsors, and welcome any questions if we've got time.
Your timing was perfect. 2
Oh,
seconds.
okay.
So,